Alright, so for quiz number 5, the first thing we've got is this equation, and number 1 asks us to balance it. So let me go ahead and write it out. That way we can have our mole-to-mole coefficients in the equation without making a big mess. Okay, here's our equation. We can now play around with the mole ratios and see what we can do to get this equation balanced. So I'm going to start over here with this molecule. You could start pretty much anywhere and it would work, but that's just a matter of personal preference. So starting out here, I got 1 sodium, and now I have 2 sodiums here. And let me write this out too. So sodium on this side of the equation and sodium on this side. So here I count I've got 2. And on this side I've got 1. Well, what I can do now is I can just double the number of sodium hydroxides I have on the left side of the equation, and now all of a sudden I have 2 sodiums. So my sodiums are balanced. Let's check our oxygens. So for oxygen we have 2 oxygens on this side, and we got 2 oxygens on the right side. So we got 2 oxygens there on both sides. That is good. 2 hydrogens and 2 hydrogens. So the hydrogens are balanced. And we've got 2 chlorines and 2 chlorines. So my chlorines are balanced. I have 2 of those. So the correct answer for number 1 is the one that has a 2 in front of the sodium hydroxide and nothing anywhere else. So the right answer for number 1 is B. For number 2, we have what I think is a little bit of a simpler equation. We got sulfur reacting with oxygen to make SO3. And we just have to make sure that we have the same number of each atom on both sides of the equation. Same thing we've always been doing. So we've got 1 sulfur here. So go ahead and write that out. 1 sulfur here, and 1 sulfur there. So the sulfurs are good, but we've got 2 oxygens here and 3 oxygens there, so the oxygens don't quite match. So what we can do is go ahead and put a 2 right here and a 3 right there, and now we have both 6 oxygens on this side and 6 oxygens on this side. And one other thing to keep in mind now is that now that I have a 2 here, I have now 2 sulfurs on the right hand side of the equation. So now I have 2 sulfurs on this side. So on the left hand side, all I need to do is put a 2 in front of this sulfur, and that gives me 2 sulfurs on that side. So now I have 2 sulfurs and 6 oxygens on both sides of the equation, and that corresponds to D. So the right answer for number 2 is D. Number 3 asks us to balance yet another equation, and this one I thought was a little bit involved. So let's start out with this molecule here. This one is probably, I think, our most complicated one. And what we see here is we've got a sodium, a gold, and 2 cyanides. So overall on this side of the equation we've got 2 sodiums, and on this side we have 1. So our inclination would be to put a 2 right here, and that would take care of both the sodiums, and we would also have 2 cyanide groups. So we've got 2 cyanides here. And that would work. But where we start to run into problems is with the oxygen. So what I did is I basically just played around with the numbers for quite a while. It took me a while to arrive to this, but essentially here's what I did. Let me write out the equation here. Gold plus sodium cyanide, oxygen, water, forming to make this complex, and sodium hydroxide. So here's what I did. I first looked at my sodiums, and I went, okay, well, I've got 2 sodiums here, and I got 1 sodium there. And I put a 2 right there, just temporarily. This is just a process, an iterative process that I'm going to have to go through. And I'm looking here, I've got 2 sodiums and 2 cyanides, and so I've got 2 sodiums and 2 cyanides here as well. So those match, but let's go to the oxygens. I only have 1 oxygen here, and I have 1, 2, 3 oxygens there. And now we have the problem of if I were to put a 3 here, let's just suppose I did that, and put a 3 right there. Now I got 4 total sodiums, and if I put a 4 right here, let me change this to a 4, so that's now a 4, and that means I've got 4 cyanides, and I only have 2 cyanides here. Okay, so let's see, I can put a 2 right here, and that gives me 4 cyanides. But now we have 2, 3, 4, 5 sodiums. We only got 4 sodiums there. If we try to put a 5 there, that's going to give us 5 cyanides, and we can't possibly have 5 cyanides here, because every time we put an integer here, it's going to multiply our cyanides by 2. So we have to make some more iterations. Let's take a look at the oxygens again. We got 1, 2, 3 oxygens here and 3 oxygens here. We also got 3 hydrogens here. We can't do that because if we have an odd number of hydrogens on this side, there's no way we can have an odd number of hydrogens on this side, because the water has 2, and each time we add on another water molecule, we're adding on an even number of hydrogens. So that puts us in quite a situation. So if I just keep on going like this and say, well, okay, what if I erase this? And let me erase this too. And I'll erase this. So I'm pretty much starting over. I go, okay, well that didn't work. Let me try something different. Let me try to keep everything so that everything has sort of even numbers of everything. So what if I put, instead of a 2 here, what if I put a 4 there, if I double it? Because if I double an odd number like 3, then I get an even number, which is 6. And I can work with a number like that because I can have even numbers of everything. So I got 4 of these, so I gotta have 4 of these. Oh, but now I have a problem because I've actually got 8 cyanides here. So let me go back and change this to an 8. So we got 8 sodiums and 8 cyanides. So I have 8 cyanides here, but I only got 4 sodiums. So maybe if I put a 4 right here, then that'll give me a total of 8 sodiums. Okay, I can work with that. And 8 cyanides. So we're back to being balanced with the sodiums and the cyanides. Now let's take a look at what happens with all the rest of the elements. So I got oxygen here, I got 4 of them, and I've got 4 hydrogens. Okay. Here I've got 3 oxygens and 2 hydrogens. Now if I can put a 2 right there, what that's going to give me is 4 oxygens and 4 hydrogens. And that's exactly what I have here. I've got 4 oxygens and 4 hydrogens. And that, I believe, now gives us the balanced equation. So let's go through and systematically evaluate this. Oh, almost. Not quite. I'll show you in a second. Let's take a look at my golds. I'll show you here what I noticed. I've got 1 gold here, and I've got 4 golds there. So what I need to do is just put a 4 here in front of the gold, and that means that now I've got 4 gold atoms on the left side and 4 gold atoms on the right side. And sodiums, we've got 8 of those, 4 here and 4 there. So I've got 8 of those here. 8 cyanide groups. And you notice I treated the polyatomic anion, this is a polyatomic anion, the cyanide group, I just treated that as one entity. And that's totally okay, because they're always going to come, this carbon and this nitrogen are always going to come together, in this case, as a polyatomic anion. So that was okay to do. I've got 8 here. And what else do I have? Oh, oxygen. Got oxygen right there. 2 and 2 make 4. I've got 4 oxygens here. And hydrogens. Where's our hydrogens? There we go. Hydrogens, I've got 4 hydrogens there and 4 hydrogens there. There we go. So the correct answer for number 3 is D. That one took forever, and that is, I would admit, that is a very complicated problem to balance. But nonetheless, the answer is D, and that's how I would go about doing it. So it is a process. It's definitely something that takes a while. It isn't always immediately obvious, so sometimes you got to go back and forth like that. But eventually you'll get to where you have the same numbers of all the elements on both sides of the equation. Okay, so for number 4, we're given this molecule and we're being asked to determine what its molecular weight is. And in order to do that, what I did is I just went to the periodic table and I looked up how much a mole of each of those atoms weighs, and then multiplied each of them by the number of them I have in the molecule. So I got 2 mercuries and I've got 2 chlorines. So basically what I'm saying here is that in 1 mole of this molecule, I've got 2 moles of mercury and 2 moles of chlorine. And I just take the molar masses of each of those elements and multiply them by 2. So altogether, if I add this up now, I'm going to find that the molar mass of the molecule now is going to be 472.09 grams of Hg2Cl2 per mole. So that corresponds to B. Okay, so for number 5, an average cup of coffee contains about 125 milligrams of caffeine. And here's the chemical formula for caffeine. So it's telling you got 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. And the question asks, how many moles of caffeine is this? Well, what I did here is exactly the same thing I did for number 4. And I went to the periodic table and I looked up what the molar masses are for each of the elements. And then I went, well, for example, I've got 8 carbons in this molecule, so I've got 8 moles of carbon in a mole of this molecule. So I can take the molar mass of carbon and multiply it by 8. So for the molecule, I'm going to have 8 moles of carbon for every mole of molecule. So when I add all of these up together, and I do the same thing, of course, for hydrogen, nitrogen, and oxygen, I would find that I have 194.193 grams of caffeine per mole. So let me jump down here to finish this problem. So now that I know how much a mole weighs, I need to figure out how much 125 milligrams weighs. So if you remember from your metric tables, 125 milligrams is just 0.125 grams. So it's just this, 125 milligrams times, for every 1 gram I've got 1,000 milligrams. That's 0.125 grams of caffeine. So that's how many grams of caffeine I have. So having this many grams and knowing how much a mole weighs, I can now figure out how many moles I have. So I would just go about it like this. I've got 0.125 grams of caffeine. That's just this. Times for every 1 mole, I have 194.193 grams. So that's a mole of caffeine. I want to be specific. So for every mole, I've got 194 grams, and multiplying these together, I can cancel my grams, and now I'm left in moles of caffeine. And if I run this through my calculator, what I would get is A. So 6.44 times 10 to the negative third moles. Or excuse me, negative fourth moles. So that's how many moles of caffeine I have in a cup of coffee. Number 6 piggybacks off of number 5 and asks simply how many molecules of caffeine is this. So now that I have the moles, I'm just going to go like this. I'm going to add onto this equation and say that there are 6.02 times 10 to the 23rd molecules. I'm sorry, that's kind of squashed in there, ran out of space. So I've got 6.02 times 10 to the 23rd molecules of caffeine for every 1 mole of caffeine. And now, of course, my moles are going to cancel, and I've got molecules of caffeine. And if I ran that through my calculator, I would find that the answer for number 6 is D. Number 7 gives us a molecule called diazepam and asks us to calculate the number of grams there are in 0.0015 moles of this drug. So what I did here was I went to the periodic table and I just found the molar masses of each of the elements that are in this molecule and calculated what the molar mass of this molecule would be. And what I found was, let me move this up a little bit, what I found was that mass would be 284.646 grams of diazepam per mole. So now, just like with the caffeine, I know how many grams a mole weighs, and now I just need to figure out how many grams am I going to have if I only have 0.0015 moles. So I'm just going to take this now and go times 0.0015 moles. So I've got that many moles of diazepam. And now my moles are going to cancel, and the grams of diazepam is going to be the units that I'm left with at the end of this calculation. So that's going to be my units right there, because my moles are going to cancel. Just like that. If I run this through my calculator, I'm going to find that the number of grams that corresponds to is 0.43. So the answer for number 7 is A. For number 8, we've got magnesium burning in oxygen, and we're asked to identify which of these is the correct balanced equation for that reaction. So the way I would like to do this is first of all to just model what the equation is. So I've got magnesium and oxygen reacting, and they're going to form some number of moles of magnesium oxide. So let me write that out in the form of an equation. So we've got magnesium and oxygen reacting to form magnesium oxide. And now I'm just left with an equation that I need to balance. So I'm going to start off by balancing my magnesiums. That's pretty easy because I've already got 1 mole of magnesium on both sides of the equation. And then the next thing I've got here is the oxygen. So on the left side I've got 2, and then on the right side I've got 1. So if I put a 2 right here, then that gives me 2 oxygens on both sides of the equation. And just now I've got 2 magnesiums on this side. I still only have 1 on this side. So what I can do is just multiply the number of magnesiums here by 2. So now I've got 2 magnesiums on the left and 2 magnesiums on the right. So just like this. And my oxygens, got 2 of those on both sides. So good. This is the balanced equation for this reaction. So we got 2 magnesiums and 2 oxygens on both sides of the equation, and this corresponds to A. So the correct answer for number 8 is A. Then once again, piggybacking off of number 8, we've got here, based on your answer from question 8, how many grams of oxygen are needed to react with 25 grams of magnesium? So we're going to go back to the strategy that we saw in the worksheet that we implemented when we looked at the sugar reaction and then also when we did the iron reaction. And we're going to start out with the mass of magnesium, and we're going to convert that mass into moles of magnesium. Remember that we need to do that so that we can relate this mass to the reaction. But we can't use masses in the reaction, we have to use moles, because the reaction gives us mole-to-mole ratios. So we convert first into moles of magnesium, and then we use the balanced chemical equation to give us moles of oxygen. And then once we know the moles of oxygen, we're going to calculate the mass of oxygen that that corresponds to. And that's going to be our answer. So let's go ahead and do that. We start out here with 25 grams of magnesium. So that is our mass of magnesium, 25.0 grams of magnesium. Now, in order to calculate the number of moles of magnesium that corresponds to, we need to revisit the periodic table and find that 1 mole of magnesium is going to weigh 24.305 grams. So just like that, our grams are going to cancel, and now we're in moles of magnesium. Now we can take this number and relate it to the balanced equation we had up in number 8. And in doing so, we can convert to moles of O2. So to get the moles of O2, we can come back up here and say, how many moles of O2 do we need in order to burn the magnesium? And we find that we have 1 mole of O2 reacting with 2 moles of magnesium. Okay, that's how we're going to use the equation. And now our moles of magnesium cancel, and we're left with moles of oxygen. Now we can visit the periodic table once again and figure out what the mass of oxygen is that corresponds to that number of moles. And we go 15.999. This is just from the periodic table, grams of O2 in a mole of O2. Okay, and I'm going to come back here and I'm going to remember that I've got O2 here, and so because of that I have to have twice that mass, because there's 2 moles of oxygen in 1 mole of O2. Okay, so I just have to have that 2 there to recognize that it's O2. So now our moles of O2 cancel, and we are now in grams of O2, and that is what we want. So if we were to run this through our calculator, we would find that the correct answer for number 9 is B. So for number 10, how many kilograms of titanium oxide can be prepared from 5.6 kilograms of titanium 4 chloride? The balanced reaction, or balanced chemical equation for this reaction is the following. So let's just make sure that this is indeed the balanced reaction. So we've got titanium 4 chloride, so we got 1 titanium here and 1 there. We got 4 chlorines and 4 chlorines, and we've got 2 oxygens and 2 oxygens. So good, we're safe to use this equation. And to start off, we've got the mass of titanium chloride. So we're going to employ the same strategy. Let me come back here. We're going to employ the same strategy that we used here, except instead of magnesium and oxygen, we're going to have titanium oxide and titanium 4 chloride. So let's go ahead and get going on this one. I'm going to try to leave that up there so that way we can relate to that strategy as we go along. So we've got 5.60 kilograms of titanium 4 chloride. And what we need to do first is convert this into grams. That way we can relate our mass to what's on the periodic table. So let's go ahead and just do that. There's 1,000 grams in a kilogram, and our kilograms cancel. So this is going to be simply 5,600 grams of titanium 4 chloride. Okay, and now we can actually get to the problem. So we have we have 5,600 grams of titanium 4 chloride. We need to figure out how many moles of titanium chloride is, because remember we have to go from the mass, the moles, so that we can then relate that number of moles to the balanced chemical equation. So we've got grams of titanium 4 chloride, and let's figure out how many moles that is. So for every 1 mole of this, we have, and I'm just getting this off of the periodic table, 189.283 grams. So our grams are going to cancel, and now we are in moles of titanium chloride. And here's where we use the balanced chemical equation. So here's our balanced chemical equation, and we need to know how many moles of titanium oxide are produced for every 1 mole of titanium 4 chloride. And we find that that is simply 1 mole titanium oxide to 1 mole of titanium 4 chloride. You go, well, but Daniel, it's just a 1-to-1 mole ratio, so can't we skip this step? No! Please do not skip this step. It is super important for you to be able to go like this and cancel out your units. If you miss this step, it will not be clear how you go from moles of titanium 4 chloride into moles of titanium oxide. So even though you're not changing any numbers here, what you are doing is that you're changing your units, and you're going from moles of titanium 4 chloride into moles of titanium oxide. Super, super important to be explicit about that, because sometimes you deal with more complicated reactions and it's not that easy, and it's really helpful if you can show that step. Okay, and our last step is to go from moles of titanium oxide into grams. So I'm going to revisit the periodic table and find that the molar mass of titanium oxide is going to be just titanium and 2 oxygens from the periodic table. So, and from the periodic table, we've got 79.865 grams titanium oxide for every 1 mole. So now our moles cancel, and we're left with grams of titanium oxide. So if I was to run this through my calculator, I would find that I would get 2,360 grams, which would just be 2.36 kilograms of titanium oxide. So the answer that corresponds to is A.